energy stored in the spring is we have to find the area underneath this graph, right? So you recall that we said work was equal to the force times the displacement. This is only true when the force is constant. So when the force is a straight line. When the force is a straight line, this force times the displacement is a true rectangle, so this is the area, right? So in fact, this work done is equal to the area, which is equal to, well, the area of a triangle, right? The area of a triangle is 1/2. The base, which is delta x, right? Displacement. And then we have to multiply the vertical height, which is this much. In this case, it's going to be the force. And if you recall from the last section, a spring has a force proportional to the displacement, right? And this was due because of the Hooke's law, right? Hooke's law says the force is equal to negative kx. Here we took the absolute value, right? Or the work being done is an external force, so we take away the negative. And then we replace this here. So it's going to be 1/2 delta x multiplied by k delta x, which is 1/2 kx squared. See this? 1/2 k squared is almost in the same format as the kinetic energy, 1/2 mv squared, right? And they're very similar. Here, the only difference is, of course, k has a different units, and x has different units. Before, 1/2 mv squared has to be the same units as joules, right? It was kilograms for mass, meters per second for velocity. And if you square this, you get kilograms times meters per second squared, or meters squared per second squared, right? You should get something similar for this here. Of course, not only similar, it has to be the same thing. We're talking about energy. First, we have to get the units for K, right? Forces in newtons. Forces in newtons has to equal to some units multiplied by the meters in the displacement. Therefore, this has to be K is newtons per meter, right? When you multiply by the meters cancels out, and newtons equals newtons. Let's put this into the K now. It's going to be equal to 1/2 newtons per meter times meters squared. Sorry, units, right? There's no half. This is going to equal to newtons times meter, which is force times displacement, which is work, or joules. Right? Everything good? Okay. And then we return, we have to probably review everything we did. Again, the work done by gravity, right? You have to take force in the equation where work equals force times displacement. This force has to be gravitational force, right? In the object falling, this work done is going to be, well, the mass times, first of all, the gravitational force is mg, right? If it falls through a height of h, then the work done is, of course, mgh, right? Now we have this allows us to apply a different method for finding velocities, right? Previously, we found acceleration and time and displacement and used that to find how fast it's going, right? Now we have work. So the work done by gravity will be used to increase the kinetic energy or to make it move faster, right? In principle, if it follows a height of h, you can think of it as acceleration because of gravity just going down using motion. Or you can think of it as an increase in the energy, an increase in the kinetic energy, right? So let's try this out. Let's get some simple numbers that we know what the answers for are, right? And let's get the height equals 20 meters. Let's put gravity as 10 meters per second squared, just so we have a good round number, right? Let's rewrite the force. Let's make the mass 10 kilograms, a good round number as well. So therefore, the force of gravity is going to equal to the mass times the force of gravity, which is 100 newtons, right? Here we have all the information we need in order to get the acceleration and therefore get the velocity at the end of this fall, right? So let's use the equations for motion we learned in the first section, right? If you use acceleration equals 10, right? We have to find how fast it's going, so it's going to be v squared equals u squared plus a 2as, right? Could you try it out and see what you get for the final velocity? If you have an answer, can you please post it in the YouTube as well? So I'll wait for your response. And we have an answer here, and the answer here given was 20 meters per second, right? Okay, so this is absolutely correct, 20 meters per second. It falls for 2 seconds, right? If it falls for 2 seconds, it will also go down 20 meters. So this is the first method we used, right? Let's use the second method, and I'll use red for this one. In the second method, we want to know how much energy gravity gave it. So it's going to be work done by gravity is going to be mgh, which is 10 kilograms multiplied by 10 meters per second squared multiplied by a height of 20 meters, right? This gives us about 2,000 joules. Now we use the second equation for kinetic energy. The kinetic energy equation we know was 1/2 mv squared. So we have 1/2 times the mass of 10 times v squared. This has to equal to the 2,000 joules, right? Now we get 2,000 times 2 is 4,000 divided by 10 is going to be 400, which is equal to v squared. You take the square roots, v equals 20 meters per second. So you get the exact same results, 20 meters per second. Doesn't matter if you use acceleration or if you use energy. You just have to know that the work done by gravity went into giving it kinetic energy, right? Next, as a review, right? What happens when you move a box towards the right horizontally? What is the work done? 0. Like we said, work done has to be multiplied by a trigonometric function, cosine, right? Because there are 90 degrees displacement and force. Cosine of 90 is 0, work equals 0. Okay, now there's one last thing. What if it's not a straight line?